Hi, I'm Guang from NS High School. In this lesson on your techniques of definite integration, we will be taking a look at something different from the previous few lessons. So if we look at the question back here, we're actually starting on a thing called the divergence theorem. So from previous lessons, whether it is from this series or other series, you may have heard of some other different things, for example the Gaussian law, Green's theorem, all those things which makes use of integration in order to find some certain things. Now, what will be so special about this time? So for divergence theorem, if you have studied something like vector calculus before, then you would very possibly have heard of this. But what is so special about this exactly? So, when you think of Gaussian law, this is something similar to that, but not exactly the same, since both of them are kind of finding its flux. But in this case, we have something more of 3-dimension or possibly even higher, right? So, when we take a look at this, first of all, we need to know what are the notations, the symbols used for the divergence theorem. So starting off, you might see something like a double integration on S, then you have f vector dot ds vector. So firstly, what does the divergence theorem work with? So starting off, you will have some kind of a space V. Now this V would probably be defined in your question, right? So this space V, it will be surrounded by some sort of area called S, alright? So of course it has to be in positive orientation. Now this enclosed by the surface area S. Now what is this F you see here? F will just be a vector field inside of it. Some examples of common fields that you might think of are, for example, magnetic fields, electric fields, and there's also other different possibilities. But F is just the vector field of it, alright? So, what else would be so special about this? So, here you realize it is more of a double integration, since S it has to be, well, the area. Well, if you can recall for your Gaussian law, that would probably just be some kind of a one-dimensional thing, right? A line or something like that. Right. So when we think of this, what can we use to find this? So in this case, we could actually change a double integration into a triple integration. Right, so what will this triple integration look like? So triple integration. Now, there are a few different forms of this that you can choose from. So let's say we use V, alright? So divergence theorem. Why would it be called a divergence theorem? Well, you have div, f vector, and then you will have dv. Alright? So this is the kind of thing that you will be looking at. So let's think about some other things that that are required for this. So first of all, you might realize after you do this operator, it becomes a scalar, right? So that's one of the things. But another thing is, what is this operation exactly? And what exactly does this give? So what this will give is so it has to be continuous, and after it is continuous, there will be your first order partial derivatives, alright? So that is what you get out of this. So how about we have some other forms, some that you might be more familiar with depending on what kind of an education system you're studying, alright? So what this will have is, let's say, once again, triple integration V. So div, you can somehow change this into a del, which some of you might actually be more familiar with, since if you know about gradient, this del here, well, that is pretty commonly used, I would say. So this is one of the forms using del, and then there's also quite a few other ways to write it depending on what you like, because you can write it as I vector, then you have partial x plus j vector partial y plus k vector partial z, then this dot f vector dv. This is also a possible way of writing it, and of course you can also write this vector in other ways. And of course, if you were to combine these two, well, that's another way. So triple integration on this v. So when you do this dot product, what you have is partial fx partial x partial fy partial y partial fz partial z, and then here dv. Alright, so this is the kind. Wait, if you want to write it in this way, there will be add. Alright, since you've already finished doing the dot product. Okay, so this is what you will see. Right, so once again, it depends on what you're given, what kind of question you're taking a look at, and then you choose what kind of form you want to use. Right, so with that is mostly what this divergence theorem is trying to say, but of course there's also other things that you might want to know, how can you get from one form to another, and this del operator here, since the del operator pretty much just means this part here. Right, so with this divergence theorem, you're finding that some kind of a flux through this. Well, you take a look at the first term, alright? So, of course, depending on what you have studied before, this might look like a few different forms, like something dot something. It could mean quite a few different things, like let's say starting from your most basic things, work done, and etc. But in this case, we're taking a look more specifically at the flux. So what kind of a flux that will be, it just depends on the question. Right, so that is pretty much an introduction to what your divergence theorem is about, what it looks like, and of course, sometimes the divergence theorem is also called your Gaussian theorem, and there's also other names for it, alright? So now that we know what this theorem looks like, let's take a look at some kind of a use that we can have for it. So of course, there are many different types of uses that you can have, and this example here is just one of them. So generally, you'll want to try to find this kind of flux with this double integration, but then sometimes you just don't have the right thing, and you have to change it into a triple integration to find your flux. Right, so we're given your f vector, and the surface of this specific volume consists of these three surfaces. Right, so this is the first, this is the second, and here's a third. So one thing you might want to know is how exactly does this look like. Now take a look at it first. This is looking something like a 3D paraboloid curve, something like that, which it kind of concaves down. So that would be kind of the shape on top, and of course, if you try to substitute in the values, the top it meets together, alright? So that is the top, and then for your second part, this side, if you realize there's no z coordinate here, but it's just a circle, so it means it connects right into a cylinder. And of course, at the bottom, z is equal to 0 is just one flat plate. Right, so now that we know what these are, what else do we have to calculate first? So of course, we want to change it into this kind of a triple integration, but then we need to know what this del dot f is. So the first thing you can try to find will be the del dot f. So what exactly would this be? We take a look at these three that were given, and of course you just do partial differentiation on them respectively. So the first one, when you differentiate xy with respect to x, you get y. Then negative half y squared with respect to y, you just get negative y. And the last one, when you differentiate z with respect to z, you just get 1. So in this case, our del dot f is very conveniently 1. Right. So let's try to find our flux. So this will be equal to, so technically you can use either of these forms, but since we already found this, we can just take a look at how we work around this. Alright? So, what's the next step? Now, in this case, since we're using triple integration, there are, once again, a few different cases, depending on the kind of question you're given. So, this question here, although it's given in Cartesian coordinates, maybe you want to consider something else, maybe not. It's your choice. But of course, we can also choose to use cylindrical coordinates or spherical coordinates. It, once again, depends on the question. But in this case, if we take a look at the shape once again, it fits a cylinder pretty well. So how about let's try to use cylindrical coordinates. And thus, we have... So when you have cylindrical coordinates, this will become r, dr, d theta, and one last thing will be dz. Alright? So an r and a theta, you spin it in a circle, then z is just how it goes up. Right. So now for its boundaries. Now z, it should be pretty easy to determine since you have the bottom and the top, which in this case, the top will be 4 minus 3r squared, alright? Since x squared plus y squared is equal to r squared, if you have learned your polar coordinates. Now, the next thing that we can determine, well, either r or theta, since r will just be from 0 to 1, given by this part here, and theta, well, since it is a full turn of this, that means theta will be from 0 to 2 pi, alright? So theta is from 0 to 2 pi, r is from 0 to 1, z is from 0 to 4 minus 3r squared. And next, we can just do a little bit of integration. So let's say this is theta, and we just put it on the outside first. And then let's say this is r, and we put it on the outside first. And we work with z first. So if we work with z first, that will just be z, substitute in these two values, which actually just gives 4 minus 3r squared. And then we just put this behind. Right, so this is what we have. Now I'll just put these two together to make it look better. So 4 minus 3r squared, then you can also choose to put the r in, dr. So once again, you integrate it, which you have 0 to 2 pi. So 4r, when you integrate it, you get 2r squared. Then 3r cubed, when you integrate it, you have 3 over 4r to the power of 4. You substitute in 0 and 1, and then you have d theta. So then you just substitute in the values, which you have 2 minus 3 over 4, 5 over 4. And since this is pretty much as a constant, so you can just integrate with respect to theta immediately, which will give you 2 pi, which overally will give you 5 over 2 pi. Alright, so that is one example of using the divergence theorem. So, in conclusion, these are the few forms of the divergence theorem that you might want to know, since if you're given this or whether you're given just f, it will be quite helpful to know these different forms so that you know which one you want to exactly use. So generally your main objective would be to calculate flux while you're given your different vector fields, and then you can differentiate them. Then for your entire volume, then you can determine how are you going to integrate it. Alright, so this one below is just an example of a usage of this. Well, you can try to understand it. Alright, so that will pretty much be it for this lesson here. I hope that you're able to understand it so far, and thank you for your watching.